2004.
5.
5.
New techniques for studying the topology and geometry of almost complex manifolds.
Excuse me?
That's not your title.
I better talk about that. New techniques for studying the geometry and topology of almost complex manifolds.
Okay. All right.
So, okay, thank you. And thanks for inviting me. I appreciate it. It's been a while since I've been here, and it's great to be back. So I'm going to just take maybe a couple minutes in the beginning to just put what I'm going to talk about in a context of some different areas of mathematics. I'll be a little bit vague without a lot of details, but hopefully it'll just connect and touch to some things you already know. So, so this little line is limiting me to how much I can talk about this. So if you have a real vector space, then there are some interesting bilinear operations you can consider on it. So for example, you can talk about an inner product, which is symmetric and non-degenerate, or you can talk about a bilinear pairing that's skew and non-degenerate, or you can talk about an endomorphism that squares to minus the identity, in other words, a complex structure on your real vector space. So this is already interesting just from a linear algebra point of view. You can talk about two such structures being compatible and study their relationships. And it's even more interesting if you don't assume compatibility. There's a lot of interesting linear algebra there. So if you assume you have these structures on the tangent spaces of a smooth manifold, then you're visiting various kind of fields of mathematics that have been studied to various degrees. So over here you have Riemannian geometry. Over here you have, well, something that's related to symplectic topology. And over here you have something related to complex manifolds.
Scott, I can't see.
Oh, I'm sorry. Could you
It's in the Japanese chalk.
Where's the
You have to write louder.
I'll just write it louder.
There's better
I love it when someone just pulls out their sword. It's like, I don't know. All right. All right. So let me just trace these. So I was saying something related to symplectic topology, complex manifolds, but actually you're not in quite those categories until you assume some sort of integrability condition. So the integrability conditions over here on this side, it amounts to having this form be closed. Over here there's an integrability condition that corresponds to having something like flatness or zero curvature. And over here there's an integrability condition that corresponds to some tensor being 0. You may have heard of it before, called the Neuenhaus tensor. I'm going to introduce it by a different name today. I'm going to denote it by this symbol, mu bar. But it'll correspond to studying complex manifolds.
Sorry, why do you say that Riemannian geometry has to do with curvature vanishing?
Well,
locally constant coefficient versions.
So I should have said
So
that
they're sort of
the existence of coordinates where these tensors become locally constant corresponds to these flatness or integrability conditions.
I see. Okay.
Good question. All right, so I'm going to focus on this, but I want to not necessarily assume this integrability condition. And what we'll see is that there's something to be learned there about the integrable case, and also it can tell us something about relationships with other. Well, I won't talk about this one, but it'll tell us relationships here. Okay, so that's the setup. So suppose I have a manifold and I have a complex structure and its tangent point. So what I can do in that case is I can look at the eigenvalues.
Complex structure.
That's a name, yeah, but I just want to.
It's a standard name.
Okay. So the standard name is almost complex structure, and the word almost is to indicate that it's not necessarily an integrable structure.
Wait, just make you call it almost complex structure? Why? Who was that?
So you can speak English.
He said
If you want to give it a different name.
say whatever he wants.
He said complex structure on the tangent bundle.
Yeah.
Okay.
Tangent vector bundle.
That might mean that the tangent bundle is a complex manifold, which this
Okay.
doesn't give you.
See, that's all right. So as not to cause confusion, I won't say that then. All right. So I'm going to look. I want to bring topology into the game. So I'm going to look. I'm going to work towards differential forms. So I'm going to work on the cotangent bundle, and I'm going to use the fact that I can break the cotangent bundle up into its eigenspaces. And when you do that, you can take the exterior algebra and look at the exterior algebra corresponding to this decomposition, and you can break the space of forms.
Well, you didn't say eigenspaces of J.
No, I didn't, but I meant it. I mean, eigenspaces of J.
If you don't know it.
Yeah, I'm sorry. All right, I'll be a little slower.
So are you assuming J is integrable?
No.
No.
It's just normal.
So this is just at a point,
Yeah. So this can be done at every point. Yeah, at every point.
but not at a compatible.
Well, it can be done at every point. It's just that you can't choose a frame which is given by coordinates.
Complex coordinates, necessarily. All right, so I like to use the word A for the algebra of differential forms. And so the space of all forms, say of degree K, can be broken up into a decomposition of spaces APQ, where P plus Q is K.
These are complex value forms.
Yeah, and I should work with complex valued forms so that I have my,
This will left hand side has to have a tensor C.
yeah, so I should put tensor C here. All right, so I have this much, and I have the exterior D operator, which goes from K forms to K plus 1 forms. And it's already been mentioned a few times, so I was going to be at this moment where I said an interesting example is take any complex manifold, and then using the coordinate charts to Cn, you can inherit this structure. But more generally, there are examples that do not come from complex coordinate charts. So,
You're going to say something?
yeah, let me be philosophical for a minute. So why do I care? Why am I making a big fuss about not assuming that it's integrable? So let's suppose for a moment that really what I care about is complex manifolds. So in there are a ton of interesting structures that you can study, and not all completely understood. And one thing you might have to do is to extend these structures, or at least ask which structures can be extended to the case where I don't assume that this is integrable. But why would you want to do that? Well, if the structure extends and some property fails that you had previously in the complex world, then you've learned something about what it intrinsically means to be in that category of complex manifolds. So we're going to see today that I'm going to give a couple examples where I try to extend some well-known discussions for complex manifolds to the non-integrable setting, and some things fail and some things don't, and it's interesting. So even from that point, I think it's worthwhile. So let's go. So we have this equation, d squared equals 0. So it turns out that this is true. You can ask, what can I gain from this equation, d squared equals 0? And you can look at the space of forms and kind of break it into a bigrading given by these p's and q's. And you can ask the question, if I have a form whose total degree is k, and I take d of it, where does it land? And a priori, it just lands somewhere on the next diagonal. But the first point that I want to make is that actually there are only 4 components for d. So the claim is that d, according to this decomposition, decomposes into the sum of 4 terms. These 2 terms, which have degree 0, 1, and degree 1, 0, and 2 more terms that have degree 2, -1, and -1, 2. So how do you prove something like this? So the first thing you might do is just check that it's true for functions. Well, when you're on functions, there's only 2 places to go, and so you have these 2 terms, then there's no room for anything else. And the next thing you might check is it true for 1 forms? Well, there's only 1, 0 forms and 0, 1 forms, and here there's only 3 places you can go, and here there's only 3 places you can go. So in each case, you get 3 terms, and the other one vanishes. Well, differential forms are generated as an algebra by the functions and the 1 forms. So that since D is a derivation, that it follows that D on any K form has this formula. So that's it. There's nothing that goes over here or over here. There are no more components.
So we can all go home and check this is proof of that fourfold case.
Yeah. Yeah. It's not, I mean, it's an algebra proof. I mean, forms happen to be generated by functions in 1 form, so it's true for any algebra that's generated in degree 0 and 1. All right, so now I want to look at this equation d squared equals 0. And it turns out d squared equals 0 if and only if the following 7 equations hold. And then there's 3 more equations that are actually just the complex conjugate of the top 3. So the 3 conjugate equations of those on the top.
So I mean, it might be worth pointing out that mu and mu bar are not differential operators. They're actually order 0.
Yeah, so that's an interesting point. So actually these 2 operators right here are linear over functions. And one way to prove that is to observe that, well, they're derivations because they're the graded component of a derivation, and they vanish in degree 0. And that's another algebra fact. If you have a derivation that vanishes in degree 0, then it's linear over functions.
Right, good.
Okay, and I should say that the rest of this, what I'm doing, going to talk about is joint work with Joanna Salusi, and we have preprint from a couple years ago, a year ago on this.
So and you actually want to sort of say, so d squared equals 0, if and but you already have d squared equals 0, right? So
Yeah, you have it.
so
And you have it, so these are all true.
yeah.
Still true.
Yep. I'm still not wrong. Okay, well, you know, when I look at these equations, you know, from an algebraic topology viewpoint or just homological algebra, this one tells me that I have a differential. This one tells me that I have a chain map. In other words, with respect to the differential mu bar, del bar is a chain map. And this one tells me that del is a chain homotopy for the differential mu bar, making del bar squared homotopic to 0. Del bar squared is homotopic to 0 via the chain homotopy, I should say co-chain homotopy, del.
Drop the bar.
Del bar. Thank you. Okay. Homotopic. And so in particular, it squares to 0 if I take the cohomology of this operator. So I'm going to start doing it. Okay? So I'm going to make a definition. I'm going to define some cohomology group in degree PQ of my manifold with respect to the structure as kernel my image. And I just have to be careful about, you know, what are my I have to mind my P's and Q's. I want to go into PQ, and I have to keep track of the operator. I'm sorry, I want to leave PQ, and I want to go into PQ. And so this, you know, P minus 1, Q plus 2, and this is...
So this is the cohomology of mu.
Yeah, I meant to put that, and I didn't. It's the cohomology of this operator.
Put parentheses around, no, wait, kernel of,
There.
thank you.
So in the integral case, this would be infinite dimensional, it certainly will serve everything.
Yeah, so in general, it's you know, it's not a vector bundle that can jump around, but if it's not, you know, so let me give some examples. So if this operator is 0, which I should have mentioned, this happens if and only if D equals del plus del bar, and that happens if and only if this MJ is a complex manifold. In that example, well, of course, this is just the 0 operator. Now I understand your parentheses question. Well, the 0 operator, its kernel is everything, its image is nothing, and so this is just the space of all forms. Nothing interesting is happening. All right, so we can do that, and now we can take advantage of this next equation, and we can define a group which, by this remark, in the integrable case, is just going to correspond to Dalbo cohomology. I'm going to make it the Q grading of in QQ is going to be the acute cohomology of this. So that's a definition. And it agrees.
That's the D-bar cohomology now?
So, yeah, I'm going to call it, the Del-bar cohomology. Thank you. So it agrees with Dalbo cohomology, something, you know, for complex manifolds, if it's integrable. Okay.
So is this finite dimensional in general?
I don't know. So I'm going to give a result later that says that in general, when
You mean when M is compact?
M is compact for the rest of this discussion, but there's some arguments I can give later that at least show when Q is 0 and Q is the dimension of the manifold, that it's finite dimensional. But let me give another example first to show that it's interesting. So I'm going to give an example of a 4 manifold called, often referred to as the Kodaira-Thurston manifold. So let me say what it is explicitly as a smooth manifold. I'm going to take the group of Heisenberg group of matrices where A, B, and C are real numbers. And I'm going to cross it with real numbers and round out by the integral subgroup cross Z. So this goes by the name of Kodaira-Thurston manifold because it was studied by both independently. First by Kodaira because it has an interesting complex structure, and then later Thurston gave it as the first example of a symplectic manifold that does not have a Kahler structure. So it's interesting from that viewpoint because it can be both complex and symplectic, but not both in a compatible way at the same time. So,
Sort of form's not J-invariant, it's J-invariant.
yeah, you just miss it. But, so it is. So, let me give some numbers that are kind of fun to compute. So one can compute
So this is complex?
well, it isn't anything yet but a smooth manifold.
Right.
But what I want to say next is that it has a complex structure that I'm going to refer to in a moment. It also has an interesting J that's not a complex manifold. Turns out it's compatible with a certain symplectic form, but that's not going to be part of the discussion. So let me say there's an integrable J for which I'm going to calculate some groups. Obviously not doing me. It's the null for it. But then there's also a non-integrable J. And I want to get the groups for both of them because there's something interesting happening. So here the groups are, when I write the number 1 or 2 in a box, I mean C1 or C2.
this is one.
So this is for this.
This is as a complex manifold.
As a complex manifold, it's ordinary double cohomology.
So, I mean, it's an explicit thing, right? You take an elliptic curve, you take a Chern class 1 line bundle over it, cut out the zero section, and then add mod out by z, where you, the action on the fibers is just multiplied by 2. Take the quotient, that's this thing. Non-trivial circle bundle over a 2 torus, and then you modify it, and then multiply it by.
I'm sorry to ask such a naive question. I mean, I'm used to seeing a double diamond.
Yeah, so I'm not going to write diamonds, I'm going to write
usually
squares.
tilted. It's just.
But if you want to, my grading is here, and you can turn it like that if you want. Okay?
The thing you're used to seeing at the bottom is the look.
This is my 0, 0.
Okay.
This is 0, 0, 1, 2, 1, 2.
Okay.
Okay? And here the numbers are.
Why is? So why?
So this is a claim, and I have.
Why is 0, 1 different from 1?
In the Kahler case, there's a symmetry.
Yeah. So the
But
point
in
is.
the non-Kahler case, this doesn't admit a Kahler metric, and it turns out that the symmetry fails.
I see. Okay.
Okay. So here, the numbers are this. And this is for a non-integrable J.
It is finite dimensional.
Well, I'm telling a little lie right now, but not a big lie.
Okay.
So this is true. This is actually true. For a 4-manifold, you get lucky. In general, when I'm working on some kind of quotient of a group, the best, and I have some kind of invariant, left invariant J, my best technique is to kind of compute left invariant cohomology. But in this example on a 4-manifold, yes, it comes out to be this, and you're in good shape. Actually, there's something even a little more surprising. You can look at all the left invariant J's that come from this group, where you pass to the quotient, and it turns out these are the only 2 diagrams you get over all the J's. And you get this one exactly when it's integrable, and you get this one exactly when it's not integrable.
So you've written out a careful proof that if you have a left invariant J on a compact Lie group, or by quotient by lattice, then in fact every class has a unique.
So I don't have a surjective argument in general on arbitrary dimensions, but in dimension 4,
It works.
yeah.
Nice.
Okay. So there's something else interesting here going on, which is that you can take this J, you can connect it by a path to this one. And what happens is you can go and compute the diagram for every point in the path. And as soon as you leave this one, this number jumps up to a 4. And this number jumps down to a 0 immediately. Now, that means that these numbers are not semi-continuous in either sense. They're not upper semi-continuous or lower, because this number is jumping up and this number is jumping down. So for those that are aware with complex manifolds have this nice feature that when you work in families of complex manifolds, the numbers are semi-continuous one way, but not the other, generally. So we learned something here, which is that being integrable, we learned something about what it means to be a complex manifold. This is a special property. Even though we can extend this definition to the non-integrable setting, we lose a property that we had in the complex setting, which in some sense can make us appreciate it more.
So the statement is that for left invariant J's on this manifold thought of as Heisenberg group times R, for left invariant J's, these are the only 2 possibilities.
Yeah.
I thought these manifolds were called Iwasawa manifolds.
No, I think that's a little
No, that's
different.
different.
I looked it up on Wikipedia, they agree.
All right.
That's where you take the complex Heisenberg group multiply the Gaussian integers.
Right.
So it's like one-dimensional.
So next, so that's kind of the end of this discussion. And the next thing I want to do is kind of try to relate this to topology. So the point is that these groups that I wrote down, this first cohomology using this first operator, and the second cohomology using this del bar operator, they're actually the first 2 in a sequence of groups that converges to the de Rham cohomology. So let me write that here. So the theorem is, given any such M, J, there's a filtration of the differential graded algebra forms such that, well, whenever you have a filtration compatible with the differential, there's an associated sequence of cohomology groups called a spectral sequence. And the statement is that for this particular filtration, the associated spectral sequence satisfies that its first page is exactly this group we were considering. And it converges to the de Rham cohomology of the manifold. So I think for a colloquium, I'm not going to get in the weeds on spectral sequences, but let me just say that there's a sequence of groups you can compute, and eventually, after finitely many terms, the claim is that this group is isomorphic to the de Rham cohomology of the manifold. So this generalizes the existence of something called the Froelicher spectral sequence for complex manifolds.
So for real dimension 4, did these degenerate in general?
Well, there's kind of a silly bound on how fast they degenerate, which is, eventually the differential leaves the page, but I don't have a better bound than that in general.
And it's a remarkable fact for complex surfaces that in fact the Froelicher spectral sequence always degenerates, but
Yeah, I don't know. It's a great question.
it's possible, that certainly in this example it seems to be.
Yeah. So there's another kind of class of examples like this in dimension 4 which don't have any integrable j's on them that you can study. This filiform Lie algebra, and they're interesting for that too. So maybe I won't say exactly what the filtration is just because of time, but I want to make a remark here, which I think is really interesting. So it turns out that when you have such a spectral sequence that every page, this is just the first one, there'll be a second one, and there'll be a third one, etc. Every page has a bigrading, and that bigrading actually comes from a filtration that's induced. Every time you take cohomology, you can kind of push the filtration forward and look at the next bigrading. So a corollary that comes out of that is that for any mj, there's a natural bigrading on the de Rham cohomology. And natural means it respects, maps of these structures. So I call these de Rham diamonds. And that should be really funny now that I don't write, you've already noticed that I don't write things as a diamond. Okay. So then there's something from this that's kind of trivial and it's kind of obvious once you say it, but it's worth saying. So if you just fix any smooth manifold, there are finitely many de Rham diamonds that occur. So there's a big infinite dimensional space of almost complex structures, huge infinite dimensional space, and there are finitely many diamonds like this.
Still almost complex.
And this works even in the non-integrable case.
But it has to admit some almost complex structure. You're always
Yeah, I guess the empty set is finite, but
Okay.
yeah, I didn't mean to do that
No, I didn't.
way, but and the point is just that you've only got so many Betty numbers to spread around, and you have to, on each diagonal, you have to make the diagonal add up to the total Betty number, and there's only so many ways you can do that. In practice, for all the computations I've done, dimension 4 and 6 and things like this, there are much fewer diamonds than you would think.
So a diamond really means this grid of integers.
Yeah.
That's what you mean by it. You don't mean the actual linear algebra.
Yeah, no, I just mean the dimensions of the spaces you can get out.
Dimensions.
So a question that I don't know how to answer, and is probably far off, is, what are they?
Is there any shadow of duality where there's a...
So if you work in the left invariant world and you only do left invariant calculations, then yes, there's duality on every page of the spectral sequence. When the general global space of forms is infinite dimensional, I don't quite know how to prove it. Kind of pairing you want to use in the infinite dimensional case doesn't quite work. But of course, with complex manifolds, your E1 page is finite dimensional. There are proofs of that. I learned one from Alec 10.
You need an analyst collaborator.
So, what time are we on? 4:50? 5? 5.
5.
5. Okay.
If the speaker's behind.
Let me ask question 2. I mean, anyone could have asked this question, so I don't get any credit for asking this, but I mean, this is kind of like anything you want to know, which is which ones occur for J intervals. That's, we'd all like to know that too. I don't have any idea. But we see in some examples that there's something going on. The one thing I can prove is that in general, on any smooth manifold, if the J is not integrable, then the number in the bottom right corner is 0.
Since the question was asked,
Yeah.
you just said that when they're integral, they satisfy something called duality. Can you
Yeah.
show what that means?
Yeah. So it means that if you reflect through the origin,
To the center.
through the center, I'm sorry, yeah, through the center, that the group here and the group here
So the
are
number there,
isomorphic. Number there is the number there.
Thank you.
And there are other symmetries that you could ask for that happen in nicer situations, like when you have a Kahler manifold, you have additional symmetries, like reflection over this line is also an isomorphism.
Oh, wait.
Those don't.
Rotate by 90 degrees. It's invariant.
Okay, I'm not doing that one. All right. Turn our heads here. All right. So.
180.
So I started with this picture of Riemannian metrics here and non-degenerate 2 forms and these J's that square to minus the identity. And then all the discussion that I've given so far is right here in this spot. I haven't introduced a metric.
We're all trying to remember what was written on the board.
There's a shadow of it.
That's okay.
G, omega, and a J. And so far I've only used the J. And you might ask, is there a discussion like that over on this side as well? Is there a way to use the general setup where we don't have the symplectic condition to study these objects in some sort of algebraic way? But what I'm going to do now is I'm going to go back to the case where I have a J, and I'm going to ask the question, is there anything it can tell me about certain metrics on a manifold? Suppose I fix one of these, can it tell me anything about certain metrics? So let me state a theorem. Suppose you have a manifold with J and a metric, and I'm going to assume the manifold for the moment is dimension 6. And for this metric, I'm going to take a connection, which is the Levy-Schmieder connection. And I'm going to suppose my manifold is closed. And I'm going to suppose that this satisfies the condition that the covariant derivative of J, so this is a connection on a tangent bundle, but I can extend it to a connection on endomorphisms of the tangent bundle. So I can differentiate this J in the direction of a vector. And that gives me a new endomorphism. And I can apply that endomorphism to any given vector. And I want to suppose that this satisfies the condition that this is skew in x and y. So that's my, my assumption. Just to relate this to a case you might have known, I mean, there's a simple case where, I mean, there's a, not simple, there's a, an obvious special case of skew, which is when this is 0, for example. When this is 0, this is called, this actually corresponds to something called.
So this is the nearly Kahler.
Kahler case.
Right. These are nearly Kahler.
Right. And so I want to not be in in this case. That's well studied. But I'm gonna assume that this is not 0. I'm going to assume it's nowhere 0. And this has a name. It's called nearly Kahler case. In fact, there's various names for it. Some people call it strictly nearly Kahler. It's a name in literature. So suppose that.
It's the same as put x equal y and give 0, right?
Excuse me?
It's the same. It's often stated in terms of saying derivative of xj applied to x is always 0.
Yes. So you can. This is equivalent to saying nabla xj of x is 0, because of course you can just take any given x, write it as the sum of two vectors, decompose it into 4 terms, and then you get the skew symmetry condition. That's another way of saying it.
What does nowhere 0 mean?
It means for every non-zero x, this is non-zero. I mean, if y is 0, this is 0. But non-zero x, non-zero y.
Or just, I mean, from the statement, it's just that there is some x and there is some y for which it's non-zero. That's actually what you want to say.
Yeah, point-wise non-zero. So there exists an x and y for which it's
For every
non-zero.
point, it's non-zero.
Yeah.
Okay.
But the claim is then, well, I didn't write down exactly what the second page is here, but I'll give you an idea of what it is in the proof. The claim is that after you go to the next page in the cohomology, this is isomorphic to the de Rham cohomology. So in spectral sequence language, you say this degenerates at the E2 term. At the second page, you're at the cohomology, and all the future pages are also still the cohomology. So this can be compared with a statement that in Froelicher that for a Kahler manifold, Froelicher spectral sequence degenerates at the E1 term. All right, so let me give some indication of how something like this is proved.
And you actually mean the direct sum, right? When you say the star over, it's implicitly you're saying that it's the sum over.
Yeah, I mean for every pair here and every pair here, these are bigradedly isomorphic. So let me give an idea of this. So first, let me just draw the, you're on a 6 manifold, so you have to draw something like this. 7? What? Oh. I'm nervous. Okay.
Interesting 7-dimensional cone of these things.
It does. 7-dimensional cone has an interesting.
Oh, it's complex.
The complex dimension, its real dimension is 6, so 0, 1, 2, 3. So the part I'm not going to say in full detail, but it's interesting in its own right, is that this hypothesis tells you that already that your J is highly non-integrable. So in particular, it means that you can find a frame of 1, 0 covectors where this operator that goes from here to here, V bar, let me call this frame. I don't want to write DZs because this is not a complex manifold, so I'm going to write some symbols like Z1, Z2, Z3, where this operator looks a little bit like, well, it looks like this. Where I, J, and K are the choices 1, 2, and 3. So in other words, you apply it to the first one, you get the wedge of the other 2 bar. You apply it to the second one, you get the wedge of the other 2 bar. 1, 2, 3, 2, 1, 3, 3, 1, 2. So this is not due to me. I actually learned this in a paper from Misha Verbitsky. Not in this language, but it's essentially the same idea. And it tells you something. It tells you that this map is an isomorphism at every point. That's special to dimension 6, actually. You can't, I mean, that's the only dimension manifold for which this map could be an isomorphism just by a dimension count. And since it's an isomorphism, its kernel is 0, its image is everything.
What?
So, since it's an isomorphism, its kernel is 0, and its image is everything. And so when you calculate, here I drew my diagram first as if I was working on all forms, but now I'm going to suppose I'm on this page of Cohomology. And so it follows that you get a 0 here and a 0 here, and the constant state here. In fact, that's always 1 on that. So if you use the fact that this is a derivation, you can use that to help you calculate what it does on wedge products. And you see that this map is injective. So its kernel is 0. And this map is injective. And with a little more work, you can show this map is injective. And so you get zeros there, there, and there. And then by some Serre duality that always holds on at least this first page where the operator is linear. When the operator is linear, it kind of has like a pointwise Hodge decomposition. I'll say that at the end. It's going to be interesting. But the point is that there's a Serre duality on this page, and you get zeros like this. And when you go to the E2 page and you try to calculate the differential on the E2 page is kind of like a knight's move on the chessboard. It's over 2, down 1. And if you look at this board, anywhere you put an arrow that goes over 2 and down 1, you're either leaving a 0 or you're entering a 0. Or you're leaving the page. And so that shows that the differential on this page is equal to 0. So D2 is 0 on E2, and that's the end of the argument. What's interesting about this is that the thing you're calculating, this page, it doesn't depend on the metric. It only depends on this. And so if you just come along with any choice of J, and it doesn't degenerate at the second page, and that tells you there is no metric making it into one of these nearly Kahler manifolds. Okay, so it's an algebraic kind of obstruction for a certain J to be compatible in this sense with a metric.
So I got confused. There is some dependence on the metric, right? Because it's the nabla of this thing is this kind of endomorph.
Yeah, it turns out, in fact, the metric is it's a very, very special metric. I mean, for example, it's Einstein. When you form a cone on this, there's a...
But I just want to understand the statement that you were making. You said that this thing doesn't depend on the metric.
I'm saying this thing you calculate, you can do this for any J, even if you don't have a metric. And you'll get a sequence of cohomology groups. And it either starts being the actual de Rham cohomology on the second page or it doesn't. And if it doesn't become the de Rham cohomology on the second page and later, then there couldn't possibly be such a metric. That's all I'm saying.
Okay.
So in that
So
sense,
it's the obstruction to the existence, it's an obstruction to existence of such a metric.
of such a metric compatible with this given J.
Thanks.
That's all. So this result is actually optimal. So there's a great example. I should have probably listed earlier that some examples of these, but actually there aren't so many. The few handful that are known are homogeneous, except for one kind of non-homogeneous one last year, I believe. So, but let me give you, I'm not going to write down the details for it, but there's two interesting examples of such structures. For this one, I don't have a calculation, but this one is with the Octonian J. And that turns out to be one of these special metric with the standard method. And it was basically for loss of time that this hasn't been computed yet. But for this example, there's another example where you take the 3-sphere, cross the 3-sphere, you think of it as SU2 cross SU2, and you put a J on it that kind of moves 3 factors on this side to 3 factors on that side, and vice versa. And then for this, you can actually calculate, because you might wonder, hey, maybe there's a better statement. Maybe it always degenerates at E1, and it turns out for this example it doesn't. So if you compute the E1, which is this, what I earlier called this Brook cohomology, you get
so B1 is always going to be 0 for these manifolds, right? Because for a different reason, because they're Einstein with positive scalar curvature. So in fact, you also know that there's another 0 there for other reasons.
B1, but not on this page. You mean on the Durham?
Oh yeah, yeah. But you know, but since you know that you're already at Durham, if there was anything that was in, if the thing above the 1 was non-zero, it would survive. So that has to be 0 also.
Right, but I guess there could be something here, right?
Yeah, it's the middle square is where anything is.
Yeah. So, yeah, I left off something. So in this case, and for this I only have a left invariant calculation, but there's a theorem that this injects into the full group. At least it injects. Don't know. I mean, even in the integrable case, it's not known that this kind of left invariant stuff calculates all the global stuff. There are lots of special cases for which it does, but in general, it's not known.
By the way, this argument, I mean, it doesn't seem, it should be just fine if your nearly Kahler manifold is actually orbifold, is a nearly Kahler orbifold. The local calculation is exactly the same. And there are huge numbers of non-homogeneous ones in the orbifold case.
Oh, I didn't know that.
I'll tell you about
Okay, great. Okay, and of course that's not the cohomology of S3 cross S3, but this is, and it happens on the next page. I'll just write it so you can see where the numbers land. They land like this. And so these are your 2 3-spheres in S3 cross S3. Okay, so in general it does not, we at least have
So once you show the arrows killing off the 3s.
Yeah, so I mean, this turns out to be an isomorphism, and
Okay.
this survives, and so those 3s basically kill each other to get 0 in the next page.
But the technique is here to, you can take the JV left invariant and then have it.
Yeah. Yeah, and I mean, of course, we want to always be able to do things in the most general setting where things aren't left invariant, but we start with mechanics. So for the last 10 minutes, let me just end with an idea of how do you get something like this? Well, it uses the fact that these kind of manifolds have kind of interesting Hodge theory. And so I'm not going to introduce that. What I want to do is introduce sort of Hodge theory that works for any kind of manifold with a J and a compatible metric. So given an M and a J and a G, and I want these 2 to be compatible. So what I mean by that is that J is an orthogonal transformation with respect to this. Then you can define, for any operator, you can take, when you write D as the sum of its components, you can take the adjoint of D and take the corresponding adjoint of each of these operators. That turns out to be up to sign the same thing as conjugating by the star operator with a minus sign. And so for any symbol you see on the board here, any delta, which is mu, or mu bar, or del bar, or del, you can define a Laplacian, which is the commutator of these two. And they take on very different properties depending on which one you use. We mentioned earlier that this operator here and this operator here are linear over functions. Yeah, and I should have said earlier that this is secretly the dual of the Neuenhaus tensor, if we know what that is. You can dualize it, you can sort of tensor it with C, extend it to complex scalars and dualize it, and it's just the sum of these terms up to a factor of 4. But if you think of it as a tensor, you might miss the fact that it has square zero components. So, because these components are linear over functions, this Laplacian is linear over functions. And you can just use linear algebra to give kind of a version of the Hodge theorem, or Hodge decomposition theorem, that over every point in your manifold, you can break the space of PQ forms up into the kernel of this Laplacian, directs on the image, directs on the image. Oh, that's okay. Sorry. Of the adjoint. So this is just kind of linear algebra going on at a point.
Is there any, in analysis there are a lot of issues with, this is point-wise at each point.
Yeah,
because
so,
it's sensorial, so it's fine.
Yeah, so this is just kind of going on at every point. Let me give a funny exercise. It's not an exercise, it's like, it's one of these things like, again, it's simple when you say it, but it's very hard to do. Find conditions for this Laplacian type operator to have a non-zero eigenvalue. Problem. That's not easy because that happens if and only if the structure is not integrable. But there are lots of theorems in geometry about certain types of, can you hear the shape of the drum and things like that. So spectrum of operators, so that's something you can ponder. Okay, so let me end with a theorem. So for any Mj, there's an inclusion from, well, you take the Delbo cohomology. And I want to look at the kernel of this operator. I kind of want to intersect its kernel with the kernel of the del bar Laplacian. So it turns out that when you intersect those kernels, because that's actually just the kernel of one single self-adjoint elliptic operator, the kernel of their sum. So this is not hard to check. Yeah, positive operators. And so the claim is that there's an inclusion there. And of course, it's an iso if J is integrable. By the del bar Hodge theorem. Because then this operator becomes 0. And in general, it is not. onto.
General what?
It is not onto in general. So in general, if you have a J that's not integrable, this may not be onto. Interestingly, these, in general, I don't know if this is
Also,
fine.
it's a piece of the cohomology.
Yeah, it's
Find out. Each metric gives you a piece of the cohomology.
yeah, it's picking off a piece. So it turns out it is an ISO for Q equals 0 and M equals, Q equals the complex dimension of the manifold. So in the bottom row and in the top row, you can actually calculate these groups using these
Operators
formulas.
are 0, right?
Well, there's lots of zeros going on, right? Because the adjoint operators leave the page this way, and then when you're in the top row, mu bar and del bar leave the page this way, and that their adjoints don't. And there's a little something to check there. You have to use a Green's operator for this, but it can be done. It's not hard.
So I thought, D is, D is del plus del bar functions, like why I would have expected.
It is, yeah, and that helps you a lot in this spot. But in general, there's non-trivial components. So I think I'm out of time, so let's stop there.
So you seem to have done a lot of calculations with left invariant J's, but if you just instead had something which is homogeneous, but not, it's not just a Lie group, does the same method work?
I hope so, but I haven't actually done calculations like that. But I hope to maybe do a calculation like that for S6, or a nice.
By manifold would be good, or
Yeah.
CP3?
Yeah.
So you had examples where there was an integrable and a non-integrable J on the Kodaira-Thurston manifold, and their de Rham diamonds were different. Do you have examples where you have an integrable, like the two
Yeah.
groups you drew would?
Yeah, okay, yeah.
Do you have examples where you have an integrable and a non-integrable J with the same diamond? That it doesn't distinguish integrable?
Geez, I might. Off the top of my head, I don't know. I've got like a zoo of, my daughter's been writing on my scrap paper. I'll look, and I'll give you an answer.
Did she go through and change all the signs?
Correct all my mistakes.
Do you have a simply stated problem that some of us could work on? Have time to work on for your daughter? Or what do you think would be?
What's the almost symplectic analog of this? I think there is one, and I think it all sits inside this generalized complex geometry. But I don't have it worked out. But that's something to think about.
So what by saying Yao, I don't know if that fits.
I'm sorry, I didn't hear
There's a guy called Yao and Seng, T-S-E-N-G, who does something symplectic world. But
Yeah.
I don't know what it is. I don't know how it relates.
Is there anything interesting that can happen in the quaternionic case where you don't have actual complex structures but bundle?
That would be another,
Like
the category that Dennis was saying that I haven't thought about, but would probably be a really good thing to
like
focus on.
S4.
Yeah, well, the interesting thing is when you pass through the twistor space, which normally you have an integrable complex structure there, but when you squash the fibers, you can make it almost, there's a non-integrable J associated with the squash version of the metric. So for example, CP3 carries in one of these nearly Kahler metrics, which is stripped in the
S4 doesn't have any J integrable or
No,
not.
that's right. But when you pass up to the twistor space,
Sure.
you can find the kind of examples that you started to.
So maybe one can apply these methods in the twistor space.
Yeah, that's correct.
So before we thank the speaker again, I want to say we have a dinner, and it's going to be a nice subsidy arrangement for professors and students. So, don't come because you're worried about paying for it.
Is it a working dinner? Dennis?
I hope so.
Yeah.
Well, I mean, within the realm, I mean, everyone should be part of it.
When you say nice, the arrangement
You wanna talk about-
the professors subsidize the students?
No, it's just Tatiana's coming
No,
out.
it's not. No,